In this section, we're going to examine oxidation-reduction reactions, which are also called redox reactions, and which are, in essence, electron transfer reactions. It's one of the two simplest kind of reactions, along with acid-base reactions. In an acid-base reaction, a proton is what is transferred, that is an H plus ion. In a redox reaction, an oxidation-reduction reaction, an electron is transferred. So it's a very small, simple particle that gets transferred, but the chemistry can be really quite complex. So in this section, we're going to look at two things, a number of things. We're going to look at what oxidation and reduction are, that is, definitions of them. We're going to look at how you can recognize oxidation-reduction reactions through the use of oxidation numbers, which is an electron counting scheme. And we're also going to look at the difference between recognizing oxidation-reduction reactions and being able to predict them. We're also going to take a short journey, if you would, not in this section, but beyond this section and frankly beyond your book, and look at some organic reactions to close out our survey of different kinds of reactions. So an oxidation-reduction reaction is an electron transfer, which means something loses electrons and something gains electrons. Oxidation is the process of losing electrons. Reduction is the process of gaining electrons. So in this example reaction here, zinc reacts with copper 2 plus to make zinc 2 plus copper. And so you can see the charge on the zinc is going up by 2. So what's really happening in this reaction is the zinc is giving 2 electrons to the copper 2 plus. So the zinc's charge goes up by 2 because it lost 2 electrons. The copper's charge goes down by 2 because it gained 2 electrons, because electrons are negatively charged. And so we say that the zinc is oxidized and copper 2 plus is reduced. Because something's gaining electrons and something's losing electrons, we can think of the reaction as happening in two halves, the thing that's gaining and the thing that's losing. And so the oxidation half reaction is the half of the reaction where something loses electrons, and that's the reaction of zinc to give zinc 2 plus 2 electrons. The reduction half reaction is the half of the reaction where something gains electrons. So in that case, in this particular case, it's copper 2 plus gains 2 electrons to make copper metal. And an oxidation-reduction reaction always has to be a combination of something losing and something gaining, an oxidation half reaction and a reduction half reaction. Much like an acid-base reaction also needs to be two halves of reaction, something donating an H plus ion and something gaining an H plus ion. So this is a fairly simple case, and another definition to add to this will be the idea of an oxidizing agent and reducing agent. So remember, the idea here is the zinc is giving 2 electrons to the copper 2 plus. The copper 2 plus can't get reduced to make copper without those 2 electrons. So zinc is the agent of copper's reduction. So zinc is the reducing agent. It's the thing that reduces the zinc. And you can say it that way. You can say zinc reduces copper 2 plus to make copper. Likewise, the zinc is losing 2 electrons, but it can't lose those electrons unless something takes them away from it. And copper 2 plus is the agent of zinc being oxidized because it's taking the electrons from zinc. So copper 2 plus is the oxidizing agent. And so an oxidizing agent is also often called an oxidant, and it's the thing that gains electrons, or you might say takes electrons from something. The reducing agent is the thing that is also called the reductant, and it's the thing that loses electrons. The oxidizing agent is itself reduced, and the reducing agent is itself oxidized. So the thing in this case oxidized is zinc, and therefore it is the reducing agent. And the thing reduced is copper 2 plus, and therefore it is the oxidizing agent. Let's look at balancing these reactions. The general idea for balancing simple oxidation-reduction reactions is that the number of electrons needs to be accounted for through both sides of the reaction, as well as just total charge. So in this case, our oxidation half reaction is that copper, I'm going to leave state symbols off, goes to make copper 2 plus 2 electrons. You know that because the copper goes to make copper 2 plus. So that's the oxidation half reaction. The reduction half reaction is silver plus an electron goes to make silver. And the reason you know it's 1 electron, how do you know that? Oh, there's not 2 there. There will be later, but there's not 2 there yet. The reason that you know that it's 1 electron for the silver is that the silver starts with a +1 charge and ends up with a 0 charge. And so therefore it must be gaining 1 electron. Now you can't add these two reactions up and leave them as is because the copper is losing 2 electrons, but the silver is only gaining 1 electron. And all the electrons need to be accounted for. So in order to have the electrons cancel, we take our reduction half reaction and we just multiply it by 2. So we'll have 2 silvers, 2 electrons, and 2 silver plus ions. So our reaction we added up is copper plus 2 silver plus ions plus 2 electrons go to make copper 2 plus 2 silver metals, the 0 oxidation state, plus 2 electrons. And the 2 electrons cancel, and our net reaction is copper plus 2 silver plus, going to make copper 2 plus 2 silvers. So that's a balanced oxidation-reduction reaction, or balanced redox reaction. The next thing we're going to do is we're going to look at more complicated compounds and more complicated ions for which the number of electrons on a particular species is not obvious. And that's using the idea of oxidation numbers. And oxidation numbers are an electron tracking method, and it's like assigning charges on atoms in molecules or polyatomic ions. So we know that we can have charges on atoms, and we know we can have charges on polyatomic things. That is like carbonate has a charge of 2-, if you would. We can also now have things that are like charges but aren't exactly like charges on atoms inside species. So if you have carbonate, the overall charge for the CO3 group of atoms is 2-. But also we're going to assign a number to the oxygens and to the carbon that relate how many electrons they have. The thing that's important is that while it's something that's like charges, they are not the actual charges. So they do not imply actual charges on atoms, and we'll mention that as we go through the rest of the examples. So there are, of course, a set of rules for doing this oxidation number assigning. And the first rule is that any pure element, just an element in its natural state, will have an oxidation number of 0. All the atoms in it have an oxidation number of 0. Any monatomic ion has an oxidation number equal to its charge. So if you have, for example, sulfur 2-, its oxidation number is 2-. In compounds that for which fluorine, chlorine, bromine, and iodine are elements in those compounds, they normally have an oxidation number of -1, kind of like the charge they would have if they were ionic. And the exception to that is if they are bonded to either oxygen or fluorine, in which case they don't have an oxidation number of -1. And so if you have, say, CF4, each fluorine in that compound will have an oxidation number of 1-. I should note, by the way, that oxidation numbers are written opposite in terms of their sign. So a charge on an S, 2-, is 2-. The oxidation number is actually written -2. I don't know why. Now, but that's the way it is. In compounds, oxygen has an oxidation number of -2, except in the peroxide ion. And the most important case of that is just the compound hydrogen peroxide, H2O2. You'll probably never see anything other than that. But H2O2, oxygen has a oxidation number -1, but almost always it has an oxidation number -2 when it's in a compound. If it was just O2, the oxidation number for oxygen in O2 is just 0, because it's just an element. Most nonmetal compounds, covalent compounds of hydrogen, has hydrogen with a oxidation number of +1. And with metals, when hydrogen is bonded to metals, it has an oxidation number of -1. And these kind of compounds are called hydrides. And you're familiar with that term from batteries, because things like nickel metal hydride is a type of battery where it has hydrogens that actually have a -1 oxidation number. But in most compounds, like, say, CH4, the oxidation number of the hydrogen is +1. And that's how it normally is. Now, there's going to be lots of times we run into atoms that aren't associated with any of these rules up here. And the way you do that is you calculate them based on the elements you do know. So calculate other atoms. Okay, so let's look at a few examples. Nitrogen in N2. Whoa, get out of there, you. Nitrogen in N2. Nitrogen is an element in its elemental form in this case, so its oxidation number is 0, as it would be for any element. Iron in the ion 3+, which is a monatomic iron, that has an oxidation number of +3, because any ion has an oxidation number equal to its charge. So those are easy. Now we're getting up to the harder parts. NO2-, there's no rule for nitrogen, but there is a rule for oxygen, and that is the oxygen has an oxidation number of -2. And the idea is the oxidation number for nitrogen plus the oxidation numbers for the two oxygens all have to add up to the overall charge, which in this case is going to be -1, because the ion has a -1 charge. The two oxygens are going to be 2 of them, because they're 2 oxygens, times -2. The -2 is each oxygen has an oxidation number -2. That's from our chart and rule number 4. And so what that means is that nitrogen, whatever its oxidation number is, the nitrogen's oxidation number, plus -4 has to add up to -1. And so what does that number have to be for nitrogen? It has to be +3. So the oxidation number for nitrogen in that case is +3. Oxygen in water is easy. The rule for oxygen is that oxygen in compounds is -2, and that's true. And so its oxidation number is -2, but actually we'd write it 2-. No, we'd write it -2. The charge is 2-. And hydrogen, by the way, has an oxidation number of -1. I'm sorry, +1. Because in most compounds, hydrogen has an oxidation number +1. Now notice that when you're assigning oxidation numbers, the fact that there are 2 hydrogens plays a role in having the charges balance, but it does not play a role in what you say. That is, hydrogen has an oxidation number of +1. The fact that there are 2 hydrogens there means that there are 2 hydrogens that each has an oxidation number +1. You don't add them up to give the overall oxidation number. This is sodium hypochlorite. It's the main ingredient, active ingredient in chlorine bleach. And so this overall is neutral, so it has to add up to 0. And you have to also recognize that it's an ionic compound, so it's Na+ and OCl-. And so the Na has an oxidation number of +1. The oxygen has an oxidation number of -2, that's the rule. And the chlorine we're going to have to find. And all that has to add up to 0. And so if you do look at that, the chlorine's oxidation number in that case has to be +1. Which is why that's an oxidant, because chlorine is normally -1, and now it's in a more oxidized state. One last example, the permanganate ion. The overall charge is -1. 4 oxygens have an oxidation number total of -8, because they're -2 each. There's 4 of them. Those are 4 oxygen atoms. And the manganese, therefore, has to be something that will add to -8 to give -1, and so that's +7. Now, this is a good example of where oxidation numbers are not anywhere near a real indication of charge. That is, if you have a permanganate ion, the charge on the manganese atom inside that ion is nowhere near +7. It might be +2.5 at the very, very most. And so oxidation numbers vary much, much more widely, both positively and negatively, than reality suggests. And what we normally do is what we really are using oxidation numbers for is to see which way they change. And so when they change, it tells us which things are gaining electrons, which things are losing electrons. But they don't really mean that those atoms in those molecules or ions have those numbers as charges. Okay, now let's return to recognizing oxidation-reduction reactions. And oxidation is the loss of electrons, but now that we know about oxidation numbers, we can add a new way of recognizing them, and that is, it's an increase in the oxidation number. Reduction is a gain of electrons, and it's a decrease in the oxidation number. That's where the reduction comes from. Its oxidation number is reduced. So let's look at this compound. It's not obviously an electron transfer reaction. And what you do is you look at the oxidation numbers of all of the elements that are in the reactants and the products, and you see which ones go up and which ones go down. So iron's an element, so it has an oxidation number of 0. I'm putting slashes through the zeros to differentiate them from oxygen atoms. Oxygen is here in its elemental form, so it also has an oxidation number of 0. Here we have a compound, In our compound, oxygen has an oxidation number of -2. That's by definition. And iron, in this case, must have an oxidation number of +3. And the reason is the 2 oxygens add up to -6. The 3 oxygens add up to -6, and therefore the 2 irons must add up to +6. And if there are 2 irons that are +6, each iron must be +3. So the iron is going from 0 to +3, so it's oxidized. The oxygen is going from 0 to -2, so the oxygen is reduced. So what you say, just say iron is oxidized. O2 is reduced. And you also say that iron is the reducing agent, because the thing oxidized is the reducing agent, and O2 is the oxidizing agent. Okay, let's look at 2 other examples. We have copper 2 oxide reacting with hydrogen. In this case, oxygen, remember, by rule is -2. Therefore, that copper must be +2. So follow that logic. You know oxygen is -2 because that's a rule. You don't know what copper is, but because the oxygen is -2 and the thing is neutral, that must be +2. Hydrogen, because this is in its elemental form, is 0. Copper in its elemental form is 0. In water, hydrogen is +1 and oxygen is -2. So notice the oxygen doesn't change. The oxygen starts out at -2. It ends up at -2. The 2 elements that change are the copper and the hydrogen. So the way you say it is you say copper atoms are reduced, but the species that is reduced is copper oxide. Say CuO is reduced. So the element reduced equals copper. The species reduced, species is a general chemical term for chemical thing. So the species reduced is copper oxide, copper 2 oxide in this case. The hydrogen is oxidized because it goes from 0 to +1, and in this case the hydrogen itself is the element that's reduced, and because it's in an elemental form, it's also the species it's the element that's oxidized, and it's also the species oxidized. So in this case, copper oxide is the oxidizing agent because it's reduced, and H2 is the reducing agent. Okay, let's look at a final example. Calcium carbonate reacts to make calcium oxide and CO2. In this case, calcium is an ion. It has a +2 charge, so its oxidation number is 2+. The oxygens are -2 each. If you figure out the carbon, the oxygens come out to 3 of them. They're -6. The calcium's +2, so this actually must be +4. If you don't get that, do it out longhand. Here, the oxygen is -2. The calcium's +2. Here, the oxygen is -2. The carbon is +4. And therefore, if we look at this, the calcium hasn't changed, the carbon hasn't changed, and the oxygen hasn't changed. And so the whole point is this is not a redox reaction. It is a reaction, but it's not an oxidation-reduction reaction. In fact, this case, it's a decomposition reaction. It has nothing to do with oxidation-reduction. But you don't know that until you actually look at the oxidation numbers to determine they have not changed. I'm going to skip that one. Now, what we just did is we talked about recognizing when a reaction you know is occurring and you know it's reactants and products, recognizing if it's an oxidation-reduction reaction. When we talked about things like acid-base reactions or precipitation reactions, you could predict whether a reaction would happen and you could predict what the products would be. That's not true for oxidation-reduction reactions. You can sometimes predict that something ought to happen, but you don't really quite know what the products will be. So these are much more diverse in what the molecules and ions will do, and therefore you can't predict products in any meaningful way other than just trial and error and just knowing things after a long time. You can, however, recognize likely things to undergo oxidation-reduction reactions. And that is that reducing agents, common reducing agents, are metals, hydrogen, elemental hydrogen, and elemental carbon. Those are things that are used very often to reduce other elements. Oxidizing agents are oxygen and the halogens, as well as some metal oxides, manganese dioxide, which is used in lots of batteries, and the chromate and permanganate ions are also used as oxidizing agents. And so reactions that involve those species are often, but not always, oxidation-reduction reactions. Some simple things to notice to recognize oxidation-reduction reactions quickly is whenever a metal reacts with a nonmetal, that's an oxidation-reduction reaction. Almost anything reacting with oxygen is an oxidation-reduction reaction, and that's where the term oxidation comes from, of course. When organic compounds undergo combustion reactions, that's a combustion reaction, that's an oxidation-reduction reaction. And there are other ones that are significantly more difficult to detect. And those are ones like this, where you look for common oxidizing or reducing agents. And in this case, permanganate is one of our common oxidizing agents. And therefore, you think when you first see that, it's probably an oxidation-reduction reaction. But you don't really know in that case until you determine oxidation numbers. Okay, so that ends our survey of oxidation reduction reactions, and now we're going to do a quick run through of some organic reactions, and we're going to do 5 of them. The first is actually also an oxidation reduction reaction. It's just combustion. So most organic hydrocarbons, in fact all hydrocarbons, that is compounds made of just carbon and hydrogen, are undergo reactions with oxygen to make carbon dioxide and water, and those are combustion reactions that are used on things like combustion engines. A substitution reaction is where one species essentially substitutes for another species. So in this case, the fluoride ion takes the place of a chloride ion. So the fluoride ion comes in, the chloride ion gets knocked out, and so fluorine has substituted for chlorine. An addition reaction is like what we called earlier a formation reaction. An addition reaction and a formation reaction are the same thing. And in this case, 2 things come together to make one thing. And the way you say it is bromine is added to this other compound, which is called ethene or more commonly ethylene. An elimination reaction is the opposite of an addition reaction, and it's a decomposition reaction where one thing breaks up into 2 things. So I'll put a plus there. And the last organic reaction is isomerization, where there's only one reactant and it just changes shape. So the same atoms, one molecule goes to make one molecule, but it's one molecule going to make a different molecule. And that ends our review of or our survey of organic reactions.